This is number 15, and I'm super mad because I went through the whole thing and I forgot to turn my microphone on, so I had to go through it twice. So it's making me very grouchy. I'm not very happy with number 15. Anyway, number 15 has some really good algebra in it, and it has a few details that I want you to pay close attention to also. So our original function was given as a quotient of two functions, so I launched into the quotient rule right away, and I did my low d high minus high d low. I drew a line and I squared below. I then distributed my 2x in, my negative 2x in over here to clean up my numerator. Once I did that, my x cubed terms canceled out, and I ended up with the first derivative of 16x over 4 minus x squared quantity squared. At this point, it's kind of important to stop and notice that at x equals 0, my first derivative would be 0. And you should understand at this point what that implies. I've got either a relative max or a relative min, possibly absolute also, occurring at x equals 0. And it didn't ask that, but it's good to know. Another thing I'm going to point out detail-wise right now is that this function has a non-removable discontinuity, aka at vertical asymptotes, at x equals plus or minus 2. This is important because where your function is discontinuous, which in this case is at negative 2 and at 2, can cause changes in concavity. So what I mean by that is, I'm going to take a little detour here. If I have a vertical asymptote at 2, it's very possible that I was concave up to the left of it and concave down to the right of it. So those need to be held under consideration when I'm going to be determining my concavity later on. I did not mention that first hour because you guys were so sleepy I was in a hurry to be done. But fourth and sixth hour, we talked about that a little bit in class. So before I continue, I'm going to kind of note that when I'm checking my concavity, I've got asymptotic behavior of the function here at plus or minus 2, and that bears consideration. So back to the problem. My next deal is I need to find where the second derivative is equal to 0, because we said that's where concavity can change. If it's greater than 0 on one side, that means it's concave up. Left means it's concave down. So I, again, because I have a quotient of two functions, did the quotient rule. Another low d high minus high d low. Be careful with your d low right here because it's a power rule, which is why this 2 came out front. And I did drop that down agreed. Don't forget to chain rule that. And we talked about that in class, so pretty safe that you did that right. I then just did a little cleanup step right here. I brought my 16 out front, and I multiplied all these terms for the second piece of the difference. Once I got to this step here, we've had this kind enough where you should go, okay, I've got a factor. So I was looking at what was in both of these terms, the one in front of the addition sign and the one in back, and I realized I had a 16 lodged in both, so I pulled that out. I also have one factor of 4 minus x squared constant to both, so I pulled out one of those as well. And we talked about how for organizational purposes it's good to put these solid brackets down. It helps you organize. It also helps you remember to clean up whatever you do in there. So when I pull a 16 out of this front term and a 4 minus x squared, really all I need is one more 4 minus x squared. And if I distribute this back in, I've got everything I need. 16 times 4 minus x squared to the second power. For my next piece of the sum, I need a 64 x squared, which is why I'm putting a 4 in to get the 64, and I'm putting the x squared in to get the x squared. I need one 4 minus x squared, and I've already got it. So that's all factored. My next step, I simply cleaned this up by saying a negative x squared plus a positive makes 3x squared, which led me to this expression right here. I then noticed I had a common factor that can cancel, which left me with, technically, fix this, left me with this right here for my second derivative. Now that's kind of frustrating because I went through the whole process because I was trying to determine where the second derivative was equal to 0, and this function here can never be equal to 0. And again, we analyze the numerator when we're trying to see what makes a function equal to 0. And no matter what I put in for x, when I square it, I'm going to get a positive. So there is no possible way that that thing's going to be equal to 0. So this whole process gave me absolutely nothing to test, which is unfortunate because it was a lot of work. And I had to do it twice because I forgot to turn my microphone on the first time. So, back to the original. What I now know is that I've got no places where the second derivative is 0, but I did have 2 places where the original function was discontinuous. So I am going to run a test. So it is good to have this function because I need to run a test on what happens to the left and the right and in between the asymptotes. So I'm going to pick something out in this region, perhaps a -3, and I'm going to see what would happen when I put it in for x into my second derivative. On the top, I'd have a positive, obviously. On the bottom, if I were to do 4 minus -3 squared, which is 9, it's going to go negative. So I'm concave down, actually, to the left of that asymptote. In between the two, the easiest to check would be 0. And if I put a 0 in for x on the top, I'm going to be positive, and on the bottom, I'm going to be positive. So I'm concave up. I also keep in mind, though, that I've got at x equals 0 relative min or max. Now thinking ahead to what's coming up next, and you don't have to get this part because I'm talking ahead of myself, but if I'm concave up and I've got a min or max, I know I actually have a min right in between the asymptotes. And likewise, when I check a positive 3 over here, I'm going to get negative for my second derivative. So what this means is the function is concave down from -infinity to -2. It's concave up between -2 and 2. And it's concave down again. At this point, I would really suggest you go to your graphing calculator and see what it looks like. And I would tell you, you probably can get, even just from this sign line, a really good, it's called curve sketching, but a really good idea of what's happening because you're concave down and you've got an asymptote. You're concave up with a min at 0, so it's probably like that. And then we've got another asymptote here at 2. So when you go graph this on your graphing calculator to get an exact view of what the function looks like, again, make sure you put these in parentheses, but I highly suggest you go put it on your graphing calculator. What you're going to see is a function that looks like, it's going to go like that. And again, this is a rough sketch, but if you did it on your calculator, you're going to see this going on with asymptotes at 2 and at -2. So, good question. It was a little frustrating, but I needed this second derivative so I could test between and to the left and the right of my asymptotes. And I am done. You guys have a great day. Number 15 has made me crabby.